Welcome to this explainer. Today we are unpacking a seriously fascinating paper titled Linking Theory and Practice, Contextualized Physics Projects in Undergraduate Engineering. This innovative work comes straight from Brazil, specifically from researchers Thiago de Assis Augusto and Octavio Mattasoglio Neto at the Maua Institute of Technology. And just to give you some context, this was actually presented at the PAEE/ALA 2026 International Conference on Active Learning in Engineering Education over in Tokyo. Let's get right into it.
So, what's the big problem we're trying to solve here? Well, the authors hit the nail on the head regarding a massive hurdle in engineering education. They state, without motivation, students tend to focus primarily on memorizing, reproducing the transmitted content, and their learning is superficial. I mean, we've all been there, right? Traditional engineering physics classes often leave students wondering, okay, but how does this actually apply to my life? That disconnect turns what should be amazing science into, frankly, just boring rote memorization.
But here is where it gets really cool. Take a look at Figure 1. This brilliantly illustrates their solution. Instead of being stuck in a traditional lab, these researchers created a contextualized physics project. Students actually use an ultrasonic motion sensor to analyze the damped behavior of real vehicle suspension systems. So instead of just crunching numbers on a whiteboard, they're physically out there pushing down on the trunks of a passenger car and a race car. They graph the damping amplitude over time to see exactly in real life how physics impacts vehicle comfort and performance. It's totally hands-on.
And this whole shift toward active, hands-on learning, it's exactly the kind of innovative framework that was celebrated at that PAEE/ALE 2026 conference in Tokyo. By bringing students into actual engineering spaces to test real machinery, these kinds of educational interventions are completely shifting the paradigm. The ultimate goal here is to promote student autonomy and make that connection between theoretical physics and practical engineering absolutely undeniable. Now, you might be wondering, does all this contextualization actually improve student outcomes? Well, before we look at the results, let's talk about their methodology, which they mapped out in Figure 2 of their research. They set up a really rigorous comparison. They took 45 undergraduate engineering students and had them complete both standard laboratory exercises and these newly designed real-world scenarios. Afterward, the students were comprehensively surveyed on both. So the million-dollar question is, when you put students in these practical environments, does it genuinely change how they learn and perceive physics? Well, if we look at Figure 3, the data reveals a really fascinating contrast. Interestingly, the students actually found the contextualized project to be a bit more demanding and labor-intensive, giving it a 3.7 out of 5 for difficulty. But, and this is a big but, it ranks significantly higher in promoting motivation, scoring a solid 3.9, and it really helped them comprehend those tricky physics concepts, scoring a 4.1. So harder work, but much better payoff. But hold on, because here is the most striking takeaway. When it came to reinforcing the connection between theory and practice, the contextualized project scored a massive 4.6 out of 5. That is a huge jump. In fact, the authors noted this was the only dimension with a statistically significant difference at the 95% confidence level compared to traditional projects. The students were literally seeing the direct link between the equations they were working with and the real-world engineering they were going to tackle in their careers.
So, to quickly summarize what we're seeing in the data, traditional LARBs often lead to superficial learning and, just memorizing for the test, leaving students struggling to see the value. On the flip side, these contextualized labs, they demand more effort and they feel more complex, but they reward students with way higher motivation and a profound, undeniable connection between theory and practice. Now, just as a quick aside, the authors did note that this didn't immediately cause a massive, statistically significant jump in overall academic grades right off the bat, but the engagement, the curiosity, and the positive shift in attitude, those were absolutely undeniable. And because this was such a success, they are already proposing new experiments. Take a look at Figure 4 here. This is a simplified representation of a motor test bench they plan to use next. The goal is to verify the linear relationship between torque and current in a direct current motor. Basically, by using a digital scale to measure torque while an AC motor imposes a mechanical load, students are going to get incredible hands-on experience with concepts like the Biot-Savart law, all within a highly relevant industrial context. How cool is that?
And to keep stripping away the abstract nature of physics, they aren't just stopping at motors. They are proposing a whole suite of new contextualized experiments for their mechanics classes. We're talking about future projects like investigating the center of mass of an actual race car, analyzing elastic behavior during material tensile tests, studying torque on a real drill press, and even analyzing linear and circular motion on a simulated production line that features conveyors and robotic arms. It's like a giant playground for future engineers.
So, as we wrap up this explainer, I want to leave you with this thought.
How can we, as educators or even just advocates for better learning, empower the next generation of engineers? How can we make every physics equation feel like it's clearly embedded in their everyday lives? Because the research from Thiago de Assis, Augusto, and Octavio Mattasoglio Neto proves that when students actually see the why behind the math, their motivation and practical understanding just absolutely skyrocket. Thanks so much for joining me on this deep dive, and I'll catch you next time.